Last time, we found the smallest number system that works. Today, your logic is too small. Find me every student studying mechanical engineering, born after the 30th of June, 1992. You already know statements. Max Mueller, matriculation number 41726, studies mechanical engineering. A statement about a concrete object. True or false, you could go check. It can't be broken down. Glue those together with and or not. Work out the truth value. That's logic, and you've got it. Now try writing that search that way. The database has 40,000 rows. You'd need 40,000 statements. And to write them, you'd need every name, which defeats the purpose. You're searching because you don't know who's in there. So here's what a search query actually is. Just this: S studies mechanical engineering. That sentence has no truth value. Not unknowns none. There's nobody in it. If it isn't true and isn't false, what is it? And why would you write it down? Watch what happens when you cut deeper. Not into smaller statements, into subject and predicate. Max Mueller was the subject. Studies mechanical engineering is the predicate. Take the subject out, leave the whole. In its place, a placeholder. Call it S. Now S studies mechanical engineering is a predicate, and S ranges over the students. One at a time, you drop a student into S. Each substitution turns the predicate into a statement with a truth value. Every S that comes out true is a hit. That's your search result. Your second condition works the same. S was born after the 30th of June, 1992. And these still combine with the connectives you know. And or not, nothing changes. So your search becomes one line. The set of S in student such that S studies mechanical engineering, and S was born after the 30th of June, 1992. Feed that in, and what comes back isn't a truth value. It's a set of students. I find this elegant. The thing with no truth value hands you something far more useful than one. So you've got a slot and a rule for filling it. But which values are allowed in? And how many have to work before the whole thing counts as true? You may think you've never written a line of logic. You almost certainly have. Out of relational database work in the early 1970s came a language for exactly these questions. SQL, structured query language. Your set of subjects goes after the keyword from. Your predicate goes after WHERE. Select star. From student S. Where S dot Studiengang equals Maskenanbau, and S dot Geburtsdatum is later than the 30th of June, 1992. Put it next to our line. From student is the set the placeholder runs over. Where is the predicate? And that and is the same connective you already know, doing the same job. Even the placeholder survived. That lonely S after student is our S. Same letter, same role. Here's the part I like. Nobody translated logic into a language. The shape of the language is the shape of the logic. It runs billions of times a day, in every bank and shop you use, and it's a placeholder and a predicate over a set. But a query hands you back the matches. Mathematics often wants a verdict instead. Does it hold for all of them, or for at least one? So predicate logic gives you new symbols. Quantifiers. They say how much of the set has to work. The first is the universal quantifier. The predicate holds for every element of the set. For all S in student, S was born after the 1st of January, 1950. No exceptions. On numbers, for all X in the natural numbers, if X leaves remainder 0 on division by 3, then X is a multiple of 3. Read it slowly. The X is your placeholder. The natural numbers are what's allowed in. The rest is a predicate. Try 300. Remainder 0 and a multiple of 3. Now try 301. Remainder 1, the if part fails, so the claim doesn't apply. The second is the existential quantifier. The predicate holds for at least one element. More is fine. There exists an S in student, such that S studies mechanical engineering. Somebody does. We're not saying who. On numbers, there exists an X in the natural numbers with X greater than 20 and X prime. True. Take 23. Bigger than 20, divisible by nothing but itself and 1. Notice how cheap that was. One number, and you've proved an existence claim forever. Nobody can take it back. Now try that with the universal one. You check 3, 6, 9, 300. How much have you proved? Nothing. There are infinitely many naturals, and you've looked at 4. The universal one claims something about an infinite set. Nobody can check infinitely many cases. So how does anyone know? There's a third one, the sharpest. You put an exclamation mark after the existential quantifier. That means exactly 1. Not at least 1. 1 and no more. There exists exactly one S in student, with matriculation number 41726. That's not an observation about the data. That's a promise the database enforces. A primary key, which is why your matriculation number exists. 2 students sharing 1 isn't an inconvenience, it's a broken sentence. Same idea on numbers. There exists exactly one X in the natural numbers with X between 8 and 12, and X prime. Let's check. 9 is 3 times 3. 10 is even. 11 survives. That's 2 claims welded together. 1, something's there. 2, nothing else is. 11 gives you the first. The dead 9 and 10 give you the second. The quantifier writes the condition. But the condition writes what your query hands back. A set is the totality of real or imagined objects, where for each object it's definitely established and can be decided whether it belongs. Hear the demand in that. Not probably. Decided. The objects that belong are the elements. A in M means A is an element of M. Strike through the symbol and it means the opposite. A is not an M. You can describe a set 3 ways. Verbally, everyone in this room. Or by listing everything in it if it's finite. M equals 2, 5, 9, 411. Or the table student. Or here's where we came in by a predicate. M is the set of X in G such that P of X. G on the left of the colon is the ground set, what's allowed in. P on the right is the predicate, what has to be true. Count the parts. Ground set, colon, predicate. That's from and where. That's our search. Let's build one and reuse the name M for it. M is the set of X in the natural numbers, with X greater than 11 and X less than 16. Feed them in. 11 fails the first condition. 16 fails the second. You're left with 12, 13, 14, 15. So M is that set. 4 elements from a sentence that named none of them. And that's the difference. The quantifiers ask a question about the set your predicate carves out. For all asks, is it everything? There exists asks, is it non-empty? Set builder keeps the set. The ground sets you'll reach for most have names. The naturals, integers, rationals, reals, complex numbers. And a predicate nothing satisfies still gives you a set. It's empty and it gets its own symbol. The sentence with no truth value turned out to be the only kind that can define anything. Everything from here starts with a hole.